So we left off talking about these different possibilities for free energy, basically how the differences in delta H versus delta S, whether they're positive or negative, how they can overall affect the free energy of the system. And remembering that free energy is basically the availability of energy in the system to do work, right? Whether that's productive work, that work usually in the regards to a chemical reaction is going to be having the chemical reaction actually occurring, giving off heat, expanding, increasing pressure, etc. Anything that's related to a chemical reaction. So that's what we're talking about when we discuss free energy. And obviously the amount of heat that's given off, or the enthalpy that's produced in that reaction, or the entropy, right, delta S, these two are going to affect whether or not we have any free energy available. And the entropy component is affected by temperature, so we have to take temperature into account when we're looking at the entropy, the overall free energy of the system. Yeah. All right, so that's where we left off. So question here is, how does delta G change with temperature, right? How does the free energy change with temperature? Right, so if we look at the free energy equation, delta G equals delta H minus T delta S. The question is, how is that going to change? It says, since reactions are spontaneous, if delta G is less than 0, the sign of enthalpy and entropy and the magnitude of the temperature matter to spontaneity. Right, so obviously, what the overall size of delta H and delta S are, as well, affect whether or not this reaction is going to be a reaction is going to occur, whether it's spontaneous or not. So let's take a look at an example of an effect of temperature on spontaneity. So the example that's used throughout the textbook is the Haber process. So we'll look at the Haber process one more time. Right, so the Haber process where we react nitrogen gas with hydrogen gas to give us ammonia. And for this reaction, the enthalpy of the reaction is minus 92.38 kilojoules, and the entropy is minus 198.3 joules per Kelvin. Now recognize again, there's differences, right? We have ones in joules, the other one's in kilojoules, so we're going to have to make a correction for that. And assume that delta H and delta S for this reaction do not change with temperature. And we've shown before that they do change slightly, but we're going to make the assumption they don't. And then we're going to predict the direction in which delta G for the reaction changes with increasing temperature. And then we're going to calculate delta G at 25 degrees Celsius and at 500 degrees Celsius. So we're going to go through first just A and predict. So we're going to answer part A by determining the sign of delta S for the reaction and then using that information to analyze the equation, right? In part B, we're going to use the delta H and delta S values for the reaction together with the equation to calculate delta G. So let's go through A first. The temperature dependence of delta G comes from the entropy term in the equation, right? So any temperature dependence is completely related to entropy, not enthalpy. So we expect delta S for this reaction to be negative because the number of molecules of gas is smaller in the products, right? So we go up here, we have one gas molecule plus 3 gas molecules going to 2 gas molecules, so 4 going to 2. So we expect our entropy component to be negative, right? A negative delta G, because we're decreasing the number of gas molecules. Because delta S is negative, minus T delta S is positive, right? So if you think about that from the equation perspective, if we have our minus T delta S over here, so minus, the temperature is always going to be a positive number, right? Because we're always above 0 K, and then we're going to be multiplying that by a negative number. So this whole component here, these two negatives are going to cancel each other, right? The negatives, I probably shouldn't use the same color pen for that, but the negatives are going to cancel each other, and you end up with an overall positive number on the right-hand side. So as you increase temperature, you're going to make the number more and more positive. So as a result, delta G becomes less negative, or i.e. more positive, with increasing temperature. So your prediction, right, is right here from the question, is which direction in which delta G for the reaction changes with increasing temperature. We predict that as the temperature increases, the delta G is going to also become more positive or increase as well, right? So the reaction becomes less favorable as you increase the temperature. Thus, the driving force for the production of ammonia becomes smaller with the increasing temperature. Overall, this reaction, the increase in temperature, you'd expect a smaller negative number or less favorable delta G. So now we're going to go on to part B, and what you can see, we can do this exact comparison, right? We're going to compare 25 degrees Celsius and 500 degrees Celsius. So we're going to be able to determine, is this true? If we increase from 25 degrees Celsius to 500 degrees Celsius, does this decrease the favorable negative number, or make the number, basically? The question is, are we going to make the number delta G more positive or less negative? And that's what you would expect. So let's go through and just simply plug in the numbers. This is missing an arrow here. Right. So here's the data, right? We're going to calculate delta G at both of these temperatures. We're given our delta H, right? We're given our delta S, and we're basically just going to be plugging in it. So here's this. So if we assume the values for delta H and delta S do not change with temperature, we can calculate delta G at any temperature using the equation 19.12. So at 25 degrees Celsius, right, we need to convert to Kelvin. So it's 298 Kelvin. We have our delta G is minus 92.38 minus 298 Kelvin times the minus 198.3 joules per Kelvin, plus our multiplying by our conversion factor to convert over to kilojoules. So we can see we have 92.38, and you can see now we go from a negative to a positive because we multiply two negatives together. Plus 59.1 gives us a minus 33.3 kilojoules of free energy available in this reaction at 25 degrees Celsius. So you would expect at 25 degrees Celsius that this reaction should proceed in the forward direction, right? Because our free energy is favorable, right? We have a negative number. So let's take a look at 500 degrees Celsius, right? 500 degrees Celsius, we need to convert over to Kelvin. It's 773. We do the math, and minus 92 minus 773 times the minus 198.3 times the conversion factor. You can see what we end up with is minus 92.38 plus, right? We can again convert over to a positive number, plus 153 kilojoules. So you can see we now have an unfavorable and free energy at 61 kilojoules. So you can see here, by increasing the temperature from 25 degrees Celsius to 500 degrees Celsius, we go from having a favorable and free energy to an unfavorable free energy. And it seems a little counterintuitive, because we're used to, for the most part, heating something up and you're increasing the reaction rate, but in this case it's not favorable. And this should be a double-headed arrow for this reaction, right? Because this is an equilibrium. Oops. So this is an equilibrium reaction here, right? Because it can go in both directions. So you can see we basically make a reaction that's more favorable going towards the left-hand side at 500 degrees Celsius. So, which, you know, and this makes sense, right? This is, you know, this is consistent with what we predicted, right? We predicted that if we increase temperature, that entropy component is going to decrease because we're decreasing the number of gas molecules on the product side, and that's directly shows up in the free energy of the system. There's one quick comment. It says increasing temperature from 298 K to 773 K, you know, changes the delta G from -33 to +61. And this makes obviously the assumption that there's no change in delta H or delta S with the temperature. You know, they do change slightly with temperature, but you know, this is going to be still going to be a reasonable approximation. We would still expect a much larger or a very positive number for the 500 degrees free energy result. And I already discussed all of this. All right. And the other thing I didn't state is that you'd expect the reverse reaction, right, to be spontaneous, and that ammonia is actually going to go in the reverse direction at 500 degrees Celsius to form nitrogen and H2. You'd expect the reverse process to be taking place, you know, at 1 atmosphere pressure. And this is the part that is something you need to take into consideration, right? Where, you know, all of these numbers, the delta H and the delta S and delta G, are all assuming a standard pressure, right? Standard pressure is 1 atmosphere. So the question is, you know, with this particular reaction, the way they run this reaction is actually by changing the pressure, by adjusting the pressure on the system. They can increase the pressure. If you increase the pressure, you're going to favor the right-hand side of the reaction, right? If you recall, we talked about systems, right? You have lots of gas molecules here in an equilibrium, and you shrink or increase the pressure by shrinking the size of the vessel, you're going to favor the side of the reaction that has the least number of gas molecules. So what they do in this reaction is they increase the pressure. So if we're adjust the pressure, that, you know, takes advantage of other properties of the chemical reactions, and therefore we're able to drive the reaction by increasing the pressure on the system. So that's how this reaction is run. It's, you know, and then they're able to increase the temperature to increase the rate of the reaction, because the rate of this reaction, again, isn't taken into account with free energy. So we don't know how fast this reaction is going, but we do know that if we increase the temperature and increase the pressure, then we can increase the production of ammonia. All right, let's go through a quick sample problem. Let's see, here we go. All right, so this is the next problem. It says the following chemical equations describe the same chemical reaction. How do the free energies of these two chemical equations compare? So think about these two different reactions and think about the free energy of each of these reactions. And then compare the two different reactions to each other. Is the free energy of one, you know, what their question is asking, right? Is the free energy of the first equation equal to the free energy of the second? Free energy of the first equal to twice the free energy of the second. Free energy of the first two times the free energy of the second, or none of the above. We got a lot of people. Got mixed answers here. Any more answers? All right, let's think about this. So when we have the free energy of our system, right, our delta G, and we're trying to determine what's going to happen to, well, should I pick on people? Ask people why they chose A and why they chose B. So you have a reaction that's essentially double, right? This reaction is twice the number of molecules, right? There's 2 times here. And the fact that there's twice the free energy, let me try to see if I can find what I'm looking for in the slide deck. Yes, this might be a good equation, right? Here, slide. I'm looking for... Oh, never mind. I'll just write it out. All right. So if you think about your delta G sub naught of the reaction, right? Delta G is going to be equal to the sum of N times the delta G of the products, right? Oops. Delta G of the products minus sum the delta G of the reactants. Right, so if we think about our stoichiometries, right, think about the stoichiometry here. So for delta G1, oops, G1, delta G not for the first reaction, we're going to have a sum, and we don't need to know the numbers, but actually we don't. Let me get rid of this sum sign. We're going to have 2 times the delta G of H2 plus 1 times the delta G of the O2 minus 2 times the delta G of H2O, right? And then for the second one, we have delta G2 is equal to 1 times the delta G H2 plus half delta G O2 minus 1 times the delta G of H2O. Oops. I know I missed something here. Oops. H delta. you can see that if we're working through trying to solve this equation, what effect is this going to have on our overall reaction? What would you expect this to look like? Anybody want to change their answers? Right. If you can see that the delta G sub 1 is going to be equal, right? Because this one is equal to twice the delta G of 2, right? Because if we just multiply this entire reaction by 2, right? If we multiply this entire reaction by 2, then this is the 1 will become 2, you know, the half will become 1, and the other 1 will become 2, right? Does that make sense? So the answer here is going to be B. Make sense? Any questions on that? Oops. All right. Questions? We'll go back to the presentation. If you pop a question in, I can always go back. Right. Let's continue on with free energy and equilibrium. So under any conditions, standard or non-standard, the free energy change can be found in this way, where we're talking about free energy of a system at, you know, any condition. So now if we move away from standard conditions, get non-standard conditions, so we're going to have a delta G. We no longer have the naught because it's not standard, so there's no little naught symbol here. And that's going to be dependent on the standard free energy of that particular system plus R, which is just a constant, times the temperature times the natural log of Q, right, the reaction quotient. So under standard conditions, concentrations are 1 molar, so Q is equal to 1, and therefore the natural log of Q is equal to 0. So this entire last part of the reaction drops out. So if we if we're talking about reactions that are being run at 1 molar, and both are run 1 molar, then this entire part of the equation just drops out here. So, but if we're not, then we need to use the entire equation. So let's go on for some examples. Oops, there's a little equation floating in the middle there. So we're going to relate delta G to a phase change at equilibrium. It says write the chemical equation that defines the normal boiling point of a liquid carbon tetrachloride, CCl4. And then, you know, the second one, it says what is the value of delta G for the equilibrium in part A. And then part C says use the data from appendix C in equation 19.12 to estimate the normal boiling point of carbon tetrachloride. So we'll go through these 3 examples. They're all related to carbon tetrachloride. First, we must write a chemical equation that describes the physical equilibrium between liquid and gaseous carbon tetrachloride at the normal boiling point. Right? The chemical equation is a change of state from a liquid to a gas. And the normal boiling point is the temperature at which a pure liquid is in equilibrium with its vapor pressure at a pressure of 1 atmosphere. So all the equation is drawn here, right? Carbon tetrachloride as a liquid is in equilibrium with carbon tetrachloride as a gas, and we're doing this at a pressure of 1 atmosphere. So this straightforward equation. So it was a really complicated way of saying we have an equilibrium between the liquid state and the gaseous state of carbon tetrachloride, and this is being run at standard pressure. All right. And because the reason we know it's standard pressure is because we want the normal, the word that they're using up here is the normal boiling point, right? The normal boiling point is the one that's being run at standard pressure, right? Standard pressure is going to be the normal boiling point. If we change the pressure, we will also change our boiling point. Because we learned that before, right? Because PV equals nRT, right? So we know that if we change the pressure here, the temperature on the other component, if we keep our volume the same, the temperature is going to be directly affected. So we can affect our boiling point by changing the pressure of a system. All right, part B. The question was, what is the value of delta G for the equilibrium in part A? So to determine the value of delta G for carbon tetrachloride in equilibrium with its vapor at normal boiling point, we're going to use the delta G is equal to delta G naught plus RT ln a Q. We're going to analyze the equation. At equilibrium, this delta G is going to be equal to 0, right? So we know that this component here is equal to 0 at equilibrium. And so any normal boiling point equilibrium, both a liquid vapor and are in their standard state of pure liquid and vapor at 1 atmosphere. Consequently, Q is going to be equal to 1, and natural log of Q is going to be equal to 0. So therefore, delta G is going to be equal to delta G naught for this process. Question is, how do we know it's equal to 0? Let me think about how to describe this best. All right, so let me see if I have 1 second to find slide deck. So we talked about it back here. Slide 34. Let me go back. Go back here. It'll be easier to explain. All right. So it goes back to when we first started talking about Gibbs Free Energy, and when we had a spontaneous reaction, right? Gibbs Free Energy is going to be negative, right, in the forward direction for spontaneous reactions. For positive delta G's, it's going to be spontaneous in the reverse direction, and then at equilibrium, the free energy of the system is equal to 0. Basically, when you're at equilibrium, you're not doing any useful work. Is basically the way to think of it, right? You're not going in the forward direction, you're not going in the reverse direction, so you don't have enough energy in the system to go in either direction. So your delta G is equal to 0 at equilibrium. That makes sense? That hopefully answer your question. But it's something you just kind of have to. It's a good question, though. Where were we? So since we're at equilibrium, and since we're talking about their standard state, the Q in this case is going to be equal to 1 because we're running everything at standard conditions. So the natural log of Q goes to 0, and delta G is therefore equal to delta G naught for this process. So we conclude that the delta G naught for equilibrium representing the normal boiling point of any liquid is going to be equal to 0, right? So whenever we're talking about, the free energy available, in a system at its normal boiling point is going to be equal to 0. We'd also find that delta G naught is equal for the equilibrium relevant to normal melting points and normal sublimation points. So whenever you're at, if you recall all of our, phase changes, all phase changes have no free energy available to them, right? There's, you're basically not seeing, it makes sense, you're not seeing productive work going on, right? You're staying at the exact same phase, same temperature, you're not having a change occur, even though there is a shift from one phase to the other. In terms of free energy in the system, the free energy remains the same. And in part C, estimate the normal boiling point of carbon tetrachloride based on available thermodynamic data. So we'll use equation 19.12 to calculate temperature when delta G is equal to 0. So we'll combine equation 19.2 with the result from part B. We see that the equality at the normal boiling point, temperature, we're going to call this temperature boiling now, of carbon tetrachloride or any other pure liquid is equal to 0, right? So whenever we have our delta G at its boiling point, it's always going to be equal to 0. So this will help explain why free energy is 0 at the boiling points and melting points, right? So solving for the equation T sub B, we obtain the T sub B is equal to delta H over delta S naught, right? The standard enthalpy and entropy. Strictly speaking, we need the values of delta H and delta S for the carbon tetrachloride, as a liquid over carbon tetrachloride as a gas equilibrium at the normal boiling point to do this calculation. However, you can estimate the boiling point by using the values of delta H and delta S for the phase changes of carbon tetrachloride at 298 Kelvin, which we obtained from Appendix C and equations 5.31 and 19.8. So you can go back and look at the chapter problem 5.31, 19.8, and we can get these numbers. Right, so we had calculated them in the past. So this is all been calculated in our past. If we calculate our delta H, right, our delta H at, remember standard, where we're using 1 mole of substance of the carbon tetrachloride as a gas minus the carbon tetrachloride as a liquid, right? And we get a plus 32.6 kilojoules for the delta H of that conversion. And then the second delta S for the exact same transformation. All these numbers are, for those of you who are trying to understand where this is coming from, all we're doing is we're taking, we're calculating the delta, H for the, sub naught of the reaction, right? Where we have the summation of the product, products minus reactants, right? N times the product, or delta H of the product, I should say, minus summation of the delta H of the reactants. That's all that we're doing on this next slide. So we're just simply getting this data from the table. You're able to calculate the delta H for this conversion. And again, we're making an assumption because we're assuming it's 298 Kelvin. But obviously the transformation for carbon tetrachloride as a liquid to a gas is not at 298 Kelvin. So these numbers would be slightly different. So we're just making a small assumption here. So we do calculate delta S using the exact same formula, just for delta S, and get the numbers from the back of the book. And you can see we end up with our delta H and delta S values that we can then plug into the equation here for TB, right? We just plug those two numbers in that we just calculated. We need to do a conversion to convert joules to kilojoules. And we can see that at the temperature boiling, you would expect it to be right around 343 Kelvin or 70 degrees Celsius. And they already said that. So if we compare that to the experimental normal boiling point, it's actually 76.5 degrees Celsius. And this is because, we made an estimate. Our estimate that we made that the delta H and delta S at 298 Kelvin are going to be the same as they are at 76.5. Right, but you can get close with your estimate, right? We can get a really close answer from 70 to 76.5, so we can get a rough idea of what our boiling point is going to be. So, and let me go back for 1 second. I wanted to make one point here. So when we're, where's the point I wanted to make? Oh, yes. So when we were talking about making the assumption that delta G is equal to 0, right? This assumption that delta G is equal to 0 takes into account the fact that we have that delta H and delta S and the temperature, right, are the delta, the temperature is dependent on the delta H and the delta S. So delta H and delta S are changing to affect this conversion, right? It's the amount of enthalpy and entropy that's changing during a phase change. The free energy stays the same during a phase change, but the enthalpy and the entropy are changing, right? We're changing the amount of heat stored, right? When we go from a liquid to a gas, our entropy is changing dramatically, right? We're going, a lot more movement going on for the molecules, and that's what's affecting that phase change. It's not the overall free energy of the system, because the enthalpy is going in the opposite direction. All right. I have a quick sample problem for this. Right. Next one. So if a reaction is exothermic and its entropy change is positive, which statement is true? Think about that. See what you come up with. Right, so I'm going to get moving on. The answer to this one is A, and I'm going to explain why in a second, right? So if we go, so A is the correct answer here. It's spontaneous at all temperatures, right? Because we have our delta G equals delta H minus T delta S, right? So what this is saying is the reaction's exothermic. So an exothermic reaction is always going to have a negative number here for delta H, and its entropy is positive. So if entropy is positive here, right, then this component right here is always going to be a negative number as well, right? So it doesn't make a difference what temperature you place into this point, you're always going to have an overall negative number for delta G, right? Because there's, what you're talking about here is you have a negative plus a negative, making a negative no matter what temperature you're at. So you need to understand, right, what probably was confusing people was the term exothermic here. You need to recognize that exothermic is referring to the enthalpy component, right? Exothermic, endothermic. You have to understand exothermic means a negative number, right? And then recognize that the entropy change is positive, means that you're going to end up with this side of the component always being negative. So this is slide 41. If you want to go back and review slide 41 in the slide deck, it covers that exact part. Sorry, I need to keep moving along here. All right, more problem. It says calculate delta G at 298 Kelvin for a mixture of 1.0 atmospheres of N2, 3.0 atmospheres of H2, and 0.5 atmospheres of ammonia being used in the Haber process. Right, so the Haber process, again, the reaction we've been using over and over again. And they give us a delta G, right, for this reaction. Right, so we use the equation delta G equals delta G naught plus RT ln of Q. And here's where Q is going to come in. So we're going to have to calculate the value of the reaction quotient for the specified partial pressures, for which we use the partial pressures from the equilibrium constant expression, right? We then use a table, I'll show you what this means in a second. We then use a table of standard free energies of formation, delta G, which is given up here now, but you would have needed to look this up to calculate that. And then we have the partial pressures, right? The partial pressures, everybody hopefully remembers back when we wrote equilibrium expressions, right? When we had, this would have been K of a pressure-based K, right? Not KC, but KP, right? Was going to be equal to the pressure of the products times its exponent, of the stoichiometry squared times the pressure of nitrogen times the pressure of hydrogen to its, stoichiometry cubed, right? So we just simply are going to plug in. So hopefully you didn't forget all of this back when we were talking about like equilibrium. It's all coming back now. So we can see here that if we take and just simply plug in the values we're given, right? We plug in the 0.5 atmospheres for the product, 1 atmosphere and 3 atmospheres for the reactants into the equation down below. And we end up with our reaction quotient is 9.3 times 10 to the minus 3. We then had already calculated the delta G is equal to minus 33.3 in problem 19.9. You can go back a couple slides and look at that. And then we're going to basically put this into equation 19.9, which is the equation right up here, right? And we're going to use kilojoules per mole as our units for delta G, right? Because we calculated this is the number of kilojoules, but we're converting this into kilojoules per mole because, right, when we ran this calculation, this was for a, right, this was standard temperature, standard condition, standard temperature, pressure, and concentration, which is the 1 molar concentration. Oops. Molar concentration, right? So we know that therefore we have minus 33.3 kilojoules for every single mole in that reaction. So we simply plug that in now. So that's the one calculation you need to make sure you understand, that you need to add that per mole in order to run this calculation, right? And this just basically makes the assumption of 1 mole for N2, 3 moles of H2, and 2 moles of NH3, right? So we then plug this into the equation. We have our delta G for the reaction is going to be equal to our delta G naught times plus RT. R is the constant here, right? This is, when you look up in the table, 8.314 joules per mole Kelvin, times the temperature in Kelvin, right? You need to make sure you have Kelvin so you can cancel the K's out. We're going to convert over from joules to kilojoules. And this is probably going to be the most common thing that people forget, is converting from joules to kilojoules times the natural log of the reaction quotient of 9.3 times 10 to the minus 3. So you can see we end up with minus 33.3 kilojoules plus a negative 11.6 kilojoules per mole. So we end up with an overall minus 44.9 kilojoules per mole for these non-standard conditions. So under the, let's go back to the question. So the question is, talking about the calculating delta G, right, for the non-standard conditions, right? Non-standard being we don't have standard pressures. We have non-standard pressures here. And we were able to calculate the non-standard pressures and see that now under those non-standard conditions, we're going to have a more favorable condition. It becomes more negative as the pressures, are changed from the standard conditions, right? Standard conditions, each of those would be 1 atmosphere. But now, because we have 1 atmosphere of nitrogen, 3 atmospheres of hydrogen, and only half an atmosphere of ammonia, we're going to favor the reaction going in the forward direction, which makes sense, right? If you think about the reaction equation here, right? If we have 1 atmosphere of N2, 3 atmospheres, and only half an atmosphere of NH3, you can see that the number of gas molecules is much larger on the left-hand side of the equation, which is going to favor a shift to the right-hand side. Right? So it makes sense that we're going to have a larger delta G under these non-standard conditions. And if we go back and think about Le Chatelier's principle would also tell us the exact same thing, right? We have increased the pressure of the reactants, H2 and the NH, to a higher pressure, to 3 atmospheres, and you decrease the amount of product pressure, so you'd expect that the reaction would shift to the right-hand side to compensate. So Le Chatelier's principle would also tell us the exact same thing. All right, I think there's another problem for this. Oops, I think I gave you the answer already. Oh, did I? No, I didn't. Actually, I posted this as the, no, I didn't give you the answer. Never mind, I gave you clues. It says, what is the temperature above which the Haber ammonia process becomes non-spontaneous? So these are the two problems that we did earlier, right? Earlier, we did this problem where we ran it at 25 degrees Celsius and at 500 degrees Celsius, and we calculated the delta G at each of these conditions, right? The delta G naught and the delta G, this is not a naught, but the other delta G are the two temperatures. So the question is, what temperature above which the Haber process becomes non-spontaneous? So how would we figure that out? Sorry, I thought I gave it away, but I didn't. So work through this problem. How are we going to figure out what temperature? Go through the calculations. Think about your equation, delta G, right? Delta G is equal to delta H minus T delta S. How does a reaction need to become spontaneous? You need a negative number, right? When does it non-spontaneous? As soon as it moves away from equilibrium. What is delta G equal to at equilibrium? This is Dominic's question, right? 0, right? At equilibrium, delta G is 0. So can everyone think of a way to what temperature? Right. I'm going to move along because I need to finish this chapter. All right. So if we think about you can keep working on it while I'm describing it. Delta G equals delta H minus T delta S. Right. So if we think at equilibrium, this is going to be equal to 0, right? And we know that our delta H is minus 92.38 kilojoules minus some temperature times minus 198.3 joules per Kelvin and times our conversion factor, which I can't fit in there, times 1 kilojoule per 1,000 joules. Right, can you solve for T? Right, hopefully everybody's solving for T by now. Right, if you solve for T, you'll find out that it's going to be 193 degrees Celsius once you convert that over into Kelvin, right? Which is you need to make sure you're doing it in Kelvin. So it's just which ends up being 466 Kelvin, right? So the answer is D. So you're just basically solving for T. I'm not going to go through all the math, but the temperature ends up being 466 Kelvin, which is 193 degrees Celsius. All right. So once you're higher than that, 193 degrees Celsius, your reaction becomes not spontaneous any longer. All right. So that's all you're doing there. Is you're just using the Gibbs free energy equation and solving for temperature. Sorry, I'm going a little quicker, but I've been going much too slowly in class. I'm falling. want you too far behind. I want at least to introduce you to electrochemistry next week. So free energy and equilibrium. So at equilibrium, the Q is equal to K and delta G is equal to 0, right? So the the equation becomes 0 equals delta G naught plus RT times the natural log of the equilibrium constant K. Rearranging this equation, the equation delta G equals minus RT times the natural log of the equilibrium of the reaction, okay? Or you can solve for K. K is going to be equal to E times minus delta G naught over RT. So all we did was basically rearrange the free energy equation at an equilibrium expression. So how can we apply this? So if we look at this, calculate an equilibrium constant from delta G. So the standard free energy change for the Haber process at 25 degrees Celsius was obtained in exercise 19.9. We got that right, which was delta G equals minus 33 kilojoules per mole. You're going to use this delta G naught to calculate the equilibrium constant for the process at 25 degrees Celsius. All right, we're going to use the equation on the last slide to calculate K. Remember to use the absolute temperature in equation 19.21 and the form of R that matches our units, right? The constant R has many different forms with the many different units, so make sure you're using the correct one. So we're just going to solve for the equilibrium constant K, right? K is equal to E to the delta G, that number that we calculated, right? It's a negative of that, times 8.314 joules per mole per Kelvin, times the temperature 298 Kelvin. So it gives us E to 13.4, which is 7 times 10 to the 5th. So our equilibrium constant in this expression is 7 times 10 to the 5th. So you can see where the equilibrium lies. At 25 degrees Celsius, it lies to the right-hand side very largely, right? So this is a large equilibrium constant, which indicates that the product, ammonia, is greatly favored in the equilibrium mixture at 25 degrees Celsius. The equilibrium constants for the Haber reaction at temperatures in the range of 300 C to 600 C are given in this table, right? They're given in the table here. These are the equilibrium constants at the higher temperatures. They're much smaller than the value at 25 degrees Celsius, right? See, right? This K is very large at 25 degrees Celsius, but you can see the temperatures they run this reaction at, the equilibrium constants are very small. So clearly a low temperature equilibrium favors the product of ammonia more than a high temperature one. Nevertheless, the Haber process is carried out at high temperatures because the reaction is extremely slow at room temperature. It's a very slow reaction, right? Because the equilibrium constant doesn't tell us anything about activation energies, right? The thermodynamics tells us the direction and extent of a reaction. It tells us nothing about the rate at which it will occur. If a catalyst were found that would permit the reaction to proceed at a rapid rate at room temperature, high pressures would not be needed to force the equilibrium towards ammonia, right? So as I mentioned before, right, they increase the pressure on this reaction, so they run it at high temperatures to increase the amount of energy available to overcome the activation energy, the EA, right? Because you're thinking, that basically we have our graph, right? We have a very high activation energy, right? And it's just this really large activation energy that we have to overcome. And that's why they need a high temperature, but they increase the pressure in order to shift the equilibrium. All right, coupling reactions. Oh, I want one last problem, but I'm going to finish this last slide. It says many natural processes would not occur alone. Nature couples them to offer the favorable energy conditions to cause something to occur, which is non-spontaneous alone, right? If we take ATP, right, for example, converting it over to ADP, right? This is the energy of life, right? ATP is converted to ADP and releases a phosphate, and that's how chemical reactions occur. But if we take that we take advantage of this chemical reaction. This is a high free energy reaction where ATP converts to ATP, right? We're going from one molecule to two molecules because we're giving off a phosphate at the same exact time. And we take this and we couple it where we release energy, and this energy is, the free energy is released, converts simple molecules, right? Some simple molecules over into different types of cellular constituents, through some type of cellular development, right? So we use the energy in the cell to make things, and ATP is the thing that does it for us. And then we couple that with another reaction, right, where we take sugar, glucose, and undergo glucose oxidation. That process releases energy by this oxidation to convert ADP back up to ADP. And in the process, we release, right, this is a favorable process because we take one molecule of glucose and convert it to carbon dioxide and water, right? And if you wanted to, you could throw another cycle on over here with plants converting, carbon dioxide and water, right? They have CO2 and water, and then they're using sunlight, right? Using sunlight as an energy source to convert carbon dioxide water into glucose. You can see everything kind of cycles round and around. So all of our energy is based on the sun hitting the planet. All right, that's the end of the chapter. We made it to the end, finally. All right, so we'll pick up on Monday with the next chapter. I'll take a look at the last problem, a couple problems that I have on the sheet, and see which ones I want to work through. But otherwise, we'll be picking up with chapter 20 on the next chapter. Any questions? Otherwise, have a great weekend. Make sure you start studying. Finals aren't that far away. Am I going to revise chapter 20 problem set? Yes, well, chapter 20 problem set isn't going to be due. Isn't usually the last chapter problem set isn't ever due, so it won't be due anyway. I'll set it, maybe release the answer key.